So our last speaker of the day we have David Butcher from MagLab, the National High Magnetic Field Laboratory. In his presentation titled Conducting the Quartet, he'll be discussing the handling of data streams with hybrid instruments. So thank you, David.
Thank you, Angela. Hi, everyone. Thanks for sticking around to the end. First, I just want to start off by thanking my colleague, Chad Weisbrod. He's the Director of Instrumentation in the ICR group, and he was very, very helpful to putting this presentation together. I couldn't have done it without him. Also, I just wanted to point out that today is a snow day at the MagLab. We're actually closed today, along with Florida State University. We had a winter storm last night, and Tallahassee got maybe 3-4 inches of snow. So these pictures are from outside my apartment building this morning, and I didn't dare go any further than that because I didn't want to slip on the ice. If you're in the southeast, I hope that you're staying warm because there's a whole lot of snow out there this morning. Okay, so the National High Magnetic Field Laboratory, or National MagLab for short, is an NSF major research facility with the goal of providing access to the highest magnetic fields for research by a global user community from a variety of different research fields. In 2023, we had over 1,800 users representing about 340 universities, government labs, and private companies worldwide. So we have a very large impact on high magnetic field research and publication globally. The lab is hosted at 3 different sites. We're headquartered here in Tallahassee at Florida State University, but we have 7 user facilities at 3 sites. Split up across here, Tallahassee, and then also Los Alamos, New Mexico, where we have our post-field facility, and Gainesville in Florida, where we have the high B/T facility and the Amherst magnetic resonance imaging facility. Today, we're going to be focusing on the ion cyclotron resonance user facility here in Tallahassee, where I'm a faculty member, where we do ultra high resolution and high mass accuracy Fourier transform ion cyclotron resonance mass spectrometry, which is a large mouthful, I know. This is the data lifecycle that was shown earlier, the CI Compass data lifecycle model, starting with data capture and going through to access, dissemination, and visualization. Because we do things a bit differently at the MagLab, I created our own kind of data lifecycle conceptualization, which starts off with proposal development and submission, which we consider to be a critical step. Data acquisition, data processing, not central processing, storage, curation, and archival, and dissemination. The lack of central processing is, and the more kind of laissez-faire, user-centric approach at the lab means that we kind of miss out on the point where a lot of metadata tagging, indexing, cataloging, and all these other functions occur for many facilities like the ones who just presented, which is one of our big challenges. We very much follow the principal investigator data structure or model that Ava pointed out in her introductory presentation. We're going to do a deep dive today into the data acquisition and processing steps for the flagship instrument in our ICR facility, the 21 Tesla ICR instrument, because I'm very familiar with it. Some of the challenges that we face in managing this instrument are kind of emblematic for the challenges of other MagLab instruments and facilities, because they also use combinations of custom, vendor-provided, and hybrid instrumentation and software. So a lot of these same issues are universal across the lab. But first, what are the primary reasons that we need FTICR mass spectrometry? Well, it's capable of very high accuracy and very high resolution, and it's particularly useful for studying samples such as dissolved organic matter, which can be found in natural waterways. This is a picture of the Suwannee River here in Florida, which contains millions of unique chemical compounds that we routinely study. Persistent organic pollutants, such as PFAS forever chemicals, which are found in things like aqueous film-forming foams, which are used for firefighting purposes, like what you can see here. Unfortunately, many DoD or Department of Defense sites, such as military bases, are contaminated with these kinds of chemicals. We can also use it for studying proteoforms through the technique of proteomics. Proteoforms are the molecularly distinct products of a single gene. Most people are familiar with the idea of a gene being transcribed into a messenger RNA and then translated into a final protein. But what you may not know is that you can actually get multiple messenger RNAs from a single gene to make multiple different sequences, and then those can all be post-translationally modified to produce a very large number, potentially, of distinct proteoforms. So in this way, you can go from 20,000 roughly human genes to millions of unique proteoforms. and we need FTICRMS to study that complexity. So how does the process work? Well, very broadly, in minimal detail, we start off by ionizing the sample of interest. Shown here is electrospray ionization, which we routinely use for liquid samples. We carry out a variety of different ion routing and manipulation techniques. Shown here is a quadrupole mass analyzer, which can be used to store, trap, and move ions from place to place. We can also do ion fragmentation to get more information about them. And then the actual analysis via ion cyclotron resonance. Now, I don't have time to explain why, but the so-called ion cyclotron effect occurs when you have ions trapped in a constant magnetic field. If you trap positively charged ions in a constant magnetic field, here the magnetic field vector is going into the screen. They will rotate counterclockwise. And we can apply an excitation factor in order to change the orbit of this rotation. Now, once we do that, we can detect the movement of those ions, which produces a variety of different sine waves, like you can see at the bottom here, depending on how fast the ions are rotating. And how fast the ions rotate is proportional to their mass to charge ratio. So what you actually get when you do a real experiment is something that looks like this. This is a combination of all of the many waves of the many ions which are rotating inside the ICR cell, something we call a raw transient or free induction decay, which is going to come up again later. So why do we need high magnetic field for these kinds of experiments? Well, the figures of merit that we're interested in, such as mass resolving power, which is the ability to distinguish species which are very close in mass, as well as the acquisition speed, all go up as you go to higher magnetic fields. In addition, things like mass accuracy, the dynamic range that we're able to study, and your peak coalescence or non-coalescence all improve as you go to higher magnetic fields. So we have instruments in our facility ranging from 7 Tesla all the way down here to 21 Tesla, our flagship instrument, which is capable of the highest accuracy and resolution of any instrument in the world, I can say, without too much overconfidence. So this is a schematic of the overall system. The actual system itself is a hybrid between a commercial instrument on the front end, which is the thermoscientific Eclipse instrument, which is connected to the ICR cell and a 21 Tesla magnet on the back end through a variety of ion optics, ion routing quadrupoles, which are shown here as these black lines. These quadrupoles are inside vacuum chambers, which are pumped out by a variety of different turbo pumps, as you can see here, in order to decrease the pressure to the ultra-high vacuum range. This is what the Orbitrap tribrid system front end looks like, as well as a schematic of the analyzers found inside it. The Orbitrap Eclipse is called a tribrid because it contains 3 mass analyzers, which are highlighted in red here. We have this quadrupole mass filter, the Orbitrap analyzer, and then the dual pressure linear ion trap. So that makes 3. By adding an ICR analyzer on the back end, we create this unique quadbrid instrument with 4 mass analyzers, which requires a lot of effort in order to manage the data streams of, which we'll talk about more in a bit. This is a shot or a couple different shots of the actual overall system. I don't really have a good way of providing the scale, but I can tell you that the magnet that you can see here is taller than me. It's about 8 feet tall. This is the Orbitrap Eclipse front end here. And you can also see turbo pumps down here that are pumping out the various components of the instrument. If we look around the side at the actual path that the ions take going from the front end of the instrument back into the ICR cell, the ion routing quadrupoles, which are roughly in line with this red dashed line, take the ions about 2 meters back into the ICR cell, which is located in this roughly in the center of this 21 Tesla superconducting magnet. And then the pressure decreases as you go to the left towards the ICR cell, down to the ultra-high vacuum region, somewhere around 10 to the minus 11 torr. Another critical component, the data station PC, shown here by this red arrow. This is the only interface that a typical ICR facility user has to the system, which is about to look a lot more complicated because I'm about to show you all of the underlying nuts and bolts. So that was the physical architecture of the system. This is a schematic showing the information flow in the cyber infrastructure architecture. So a typical purchaser of an Orbitrap Eclipse system would never have to deal with this and wouldn't have something nearly as complicated because the system would be more or less self-contained. But this is a highly custom system. So on the left are the components that are included inside the Orbitrap Eclipse system itself. And on the right, we have external components which we need in order to kind of marry this fourth mass analyzer, the ICR analyzer, onto the back. Oh, 1 second. Sorry, my headphones just turned off. So we have the Eclipse on the left, external components on the right. The components which are underlined, like lens backplane 2 and the LAN hub and whatnot, those are all custom components which are not part of the typical consumer architecture. So FTPC1 and PowerPC are both Linux systems, and lens backplane 2 and lens backplane 1 are required in order to control the voltages on the ion optics. And by ion optics, I just mean devices that are used to channel and manipulate and move the ions from place to place. All of this, the internal components, are connected via a LAN hub with TCP/IP connections to both the data station PC, which is, like I said, where users actually interact with the system, which is a regular Windows PC, and then an additional completely custom system called FTPC2, which is what actually handles the data coming out of the ICR mass analyzer, another Windows system. So that system, FTPC2, is connected via a PCI Express connection to the components in this National Instruments PXI chassis, which include things like the digitizer, which converts the analog ICR signal, that free induction decay that I showed you before with all the waves, that gets digitized here and then sent to FTPC2. Now, at this point, this is where we have the form of data that we refer to as a .dat file, which is a proprietary file format which contains the digitized transient. This is the first thing that you could really call data. It is the rawest, least processed form of the data. That raw transient gets data reduced and sent all the way through to FTPC1 for further processing, where it then gets a fast Fourier transform and other processing steps, and then sent back to the data station PC in order to be incorporated into the final file format, which is this .raw file, which is a thermo proprietary file format. This is a little bit more of a detailed schematic about how that data processing works. So this is the FID, the free induction decay that I showed you before. This undergoes processing and Fourier transform to yield what we call a frequency domain spectrum. And then that undergoes calibration in order to generate an actual mass spectrum, wherein the peaks correspond to species of a unique mass to charge ratio. This is what users are interested in, and this is what oftentimes is referred to as the raw data, even though this thing on the left that I'm showing you here, the FID, is actually the rawest data. So that raw transient goes into the .dat file. The completed mass spectra go into a thermo raw file. And both of those files eventually find their way into what we call our first, theoretically, storage architecture, which is supposed to be kind of the drive of this whole thing. The .dat file can also be utilized for our custom in-house analysis software referred to as Predator analysis. And then the thermo raw file can be directed into thermo workflows because they have a whole software ecosystem that you can use to analyze the data. Or it can be converted to an open standard file format called MZML, and then utilized for custom workflows. Or sometimes the thermo raw file can go directly into those custom workflows. So we've kind of got two dueling data streams here, the .dat files and the raw files, which have different uses and different purposes. Although, again, this mass spectrum and the thermo raw files are oftentimes the only thing that users are seeing. However, the .dat file is still useful to keep, it's useful to maintain, because it is raw and unprocessed. And theoretically, if you have a .dat file and you're able to recreate your processing steps, you can perfectly recreate the mass spectrum. And in some cases, you can actually process the .dat file better in order to generate an improved mass spectrum. So the .dat file is really something that's important to us and that we'd like to keep for future reprocessing and data mining purposes. And both these things wind up in our first, in quotation marks, storage architecture. So what's the storage architecture like? Well, currently it's very unsophisticated. It's unfortunate that the presentations before this one had some very sophisticated user portals and storage architectures because we don't really have anything that measures up. So this data management map that I created to kind of understand the data flows is already completely outdated because we've had to change or eliminate certain aspects of this system. The original data is typically born on and remains on the data station, like what I showed you before. Previously, these things were automatically backed up to a backup array that we had, but this array is going away because of increasing data volume requirements and the complication of maintaining it, as well as cybersecurity concerns. The magnetic tape backup that we've relied on is also not going to be as useful in the future because it's the storage requirements are getting too large and the system is getting too expensive to maintain. So this is going to be going away. Really, the primary archive that we have is actually just a Windows share folder, a Windows shared network drive, which is assigned the letter Z. Our component of it is Z/ICR. So people manually transfer data there for archival, which is theoretically indefinite, but we don't really have a good plan for the long term as to how to maintain this. People also manually maintain their own kind of personal archives. The most common way for a user of our facility to actually get a copy of their data is through physically taking a copy with them when they leave or having it sent to them through something like Google Drive or Dropbox. So there's really no cataloging, indexing, metadata tagging, the kinds of things you'd want to happen to enable fair data and many different other useful things to track provenance, integrity, etc. So major shortcomings, a couple of which I've already kind of mentioned. Enabling fair data and metadata. We have this problem of missing metadata. These are things like the sample information and provenance, information about the operator who generated the sample or collected the data. For some samples, we're interested in geolocation data. If it's an environmental sample, something from a river or water from an area where there's been an oil spill or something along those lines. None of that information is currently captured or tagged along with the data. We want to facilitate machine actionability because that's another important part of the FAIR principles, of course, but currently don't have any good way of doing that systematically. We also are not able to handle large and increasing data volumes and densities. This has been exacerbated by our new instrument developments. The ICR, the Eclipse front end that I showed you earlier is actually a new addition, which allows us to collect better data more rapidly, but which unfortunately, that just grows our data volume problem. And we recognize that as the amount of our archive data grows, the potential for data mining increases, which is not something we're currently able to take advantage of. Yet another shortcoming. And then on top of that, information assurance. There's new information assurance guidance focusing on data management and curation. We want to be able to enable user access and facilitate machine learning and high-performance computing applications, but this introduces some security concerns. So many of you have probably seen this by now, but NSF's new research infrastructure guide draft that was released earlier this month outlines the needs for an information assurance program and specifically mentions the importance of integrating information assurance with data management and curation efforts, which ties into what we're trying to do in the ICR facility with managing our data and getting it into a better system. All the new cyber infrastructure that we develop for handling data generated by our research infrastructure, like the 21T system, has to consider information assurance to address the evolving threat landscape, according to the RIG. We think this is particularly important for well-annotated FAIR data, which could be easily reused by data thieves, which is not really a common thing. Holding data ransom is much more common than it actually being stolen and reused, but something we published in a paper a couple of years ago is that this potential for theft for the explicit purpose of reusing it could be something that increases in the future. So, given those shortcomings, what are some of the future solutions that we're thinking about implementing in the ICR facility? Well, Ideally, we would have a system that would allow us to get data directly off of the 21T or other instruments as it's generated and transfer it into a dedicated database, which would have the capabilities for incorporating the missing metadata, which would have to be collected directly from users, which would allow it to be indexed, cataloged, resilient, something more sophisticated than a Windows shared network drive. We also want to enable high-speed access for high-performance computing and machine learning applications, potentially cloud-based analysis and visualization. Perhaps facility staff could make their own analysis scripts or software available to users so that they could use them directly. And fundamentally, we also just want access for project collaborators. Right now, even though we have user-facing systems like our user proposal system, which allows people to request instrument time, there's no way to actually get the data from those systems. It has to be done manually by working with facility staff, which is not ideal because it takes time and effort from our staff, and also because it prevents the user from getting access to the data again in the future. We also are interested in potentially broadening out this solution to other MagLab facilities. Although I talk a lot about ICR here, a lot of these solutions could also be implemented for NMR, for AMRIS, for various other facilities. ICR by far has the greatest volume and complexity of data of any MagLab facility. So if we can make it work for ICR, it's very likely that we can make it work for other facilities. We routinely generate files which are on the order of gigabytes, whereas other facilities are generating kilobytes of data because it's simple columnar plain text data, which doesn't take up a lot of space. So in order to actually get the data from the systems, we would have to, and this is the cyber infrastructure that I showed earlier, in order to actually get the data off a system like the 21T, we would need additional custom software components either on this data station PC where the raw files live, or FTPC2 where the DAT files live, to transfer the data after analysis is complete, or ideally stream it in real time to allow it to be cataloged, indexed, available, and to ensure its integrity. And like I mentioned before, this missing metadata needs to be provided by users, but we need a very low activation barrier in order to get them to actually comply and input the data that we need. We're thinking along the lines of a standalone GUI application or a web-based form, which could provide the ease of use that we want. And we've already worked on a prototype of a form to ingest that experimental metadata and to format it and put it into a JSON-LD format that's ideal for our purposes. This is just a very, very early prototype, but this is the kind of thing we're thinking about where it could be easy enough for users to actually put the data in that they would we'd actually be able to hold them to it and police it to some extent. So we're very early on overall in the process of revamping our CI, and we're quite a bit behind other facilities, but we're hopeful that by seeking out grant funding and convincing NSF that we need money for it, that we can get the resources we need to actually build that new CI. And that's all I've got. Happy to take questions.
Thanks so much, David. I'd like to open it up for questions.